Nur Zulifa Humaira binti Muhammad Ishaq, and today I will be presenting on the topic of logic gates and truth table for our discrete structure subject BITI 1233. Today, we will be covering what logic is, the 6 fundamental logic gates, AND or NOT, XOR, NAND and NOR, their truth table and how they are applied in our everyday lives. So, without further ado, let's get started. So, before we dive into the gate themselves, let's understand what exactly is logic. Logic is the foundation of how every computer thinks and makes decisions. It uses only two values, 1 which means true and 0 which means false. This is called the binary system, the language that every computer understands. Now, logic gates are the basic building blocks of all digital circuits. They take these binary values as input, process them, and produce an output. By combining different gates together, we can build complex decision-making system from a simple calculator to a smartphone to an entire AI system. This concept was actually introduced by a mathematician named George Boole, and that's why the math behind logic is called Boolean algebra. So, every app, every game, every website that you use, it all runs on billions of these logical decisions happening every single second inside your device. That's the power of logic. Alright, first up, the AND gate. The AND gate is simple. It only outputs true when all of its inputs are true. Both must be 1. If even one input is 0, the output will be 0. Look at the truth table here. A is 0, B is 0, the output will be 0. When A is 0, B is 1, it's still 0. When A is 1, B is 0, it's still 0. Only when A is 1 and B is 1, the output becomes 1. Think of it like ATM machine. To get access to your money, you need two things, which is your card and your PIN. If you have your card but wrong PIN, denied. If you have the correct PIN but no card, also denied. Both conditions must be true for you to get access. That's exactly how the AND gate works. It's strict in its everything. We have the NOT gate. And this one is probably the most simple gate of all. The NOT gate only has one input and all it does is flip the value. If we give it a 1, it gives back a 0. If we give it a 0, it gives back 1. It's the opposite, always. In our truth table, when A is 0, the output is 1. When A is 1, the output will be 0. Simple as that. A good real-life example is automatic street lights. During the day, the daylight sensor detects lights, so the value is 1, meaning it's daytime. The NOT gate flips that to 0, so the street light stays off. But at night, the sensor reads 0, the NOT gate flips it to 1, and the light turns on automatically. So, basically, the NOT gate does one job. It just says whatever the opposite of whatever it receives.
Hi everyone, my name is Nur Salia and today I will be walking you through the OR logic gate. Let's take a look at this table. The gate output is true if at least only one input is true. Think of it like a home burglar alarm. The alarm would be triggered if either the front door or the window sensor is breached. If both sensor is off, the alarm stays off. Now, let's take a look at the MATLAB script. We need to define the inputs for the door and the window sensor. Using the bitewise OR operator, the code checks the truth table. When we run the application, the output confirms our logic. If either the sensor is 1, the alarm triggers, and all safe when both inputs are 0. Let's look at the XOR or exclusive OR gate. This is XOR table. Unlike the standard OR gate, XOR outputs is true only when exactly one input is true, but not both. A perfect real-life example is ordering a meal combo. The deal says you can choose either salad or fries with your meal, but you can have both for the same price or the same meal. Now looking at our MATLAB code for the meal combo, we utilize the XOR AB function when we execute the code. The truth table output clearly shows selecting just salad 0, 1 or fries 1, 0 results in order OK. However, trying to take both 1 for 1 or choosing neither 0 for 0 results in invalid order.
Hello everyone, my name is Ku Chiu Mei and I am here today to talk about two fundamental logic gates, the NOR gate and the NAND gate. First, let's start with the NOR gate first. The NOR gate is like a strict off switch. If you look at the truth table on the screen, you will see that the output is only 1 when both input are 0. Even if one input is 1, the output immediately becomes zeros. Think of this is a quiet room sensor. The room show quiet, which is our output is only 1 when no noise sensor are triggered, but as soon as any noise occurs, the quiet status disappears and the output becomes 0. It is a perfect example of a system that only gives a yes when there is absolutely no interference. It is very simple, but we serve keeping system safe and stable. Next, let's look at the NAND gate. For the NAND gate, the NAND gate work is a different way. It is basically the opposite of a AND gate, and as you can see in the truth table, the output is 1 in almost every case, but the output only becomes 0 when both input are 1. You can think of this as a game access slot. This system let you play, giving you an output of 1 most of the time is only blocks you given you an output of 0 when all security conditions are met. For example, when two different approval buttons are pressed at the same time. Because the NAND gate can be used to build any other type of logic circuit. It is famous for being a universal gate. It is arguably the most important piece of logic used inside your computer CPU.
Hi everyone and greeting to our lecturer. My name is Nurantasha binti Mazhar Hussein as the final presenter for our group. I am excited to show you how all the theory we have discussed so far actually apply to the real world. Have you ever wondered how electronic devices make decisions? The truth is logic gates are absolutely everywhere. They are hidden in plain sight. Forming the foundation brain of daily technology like password, security system, burglar alarm, automatic straight line, and even advanced computing system. Every digital devices around us is constantly running this logical parameter. At our first constraint example on page 10 on the flip book, a smart door lock which utilizes an NAND gate. For a high security door, you might need two sectors to gain entry, a correct password which we can call input A and a correct fingerprint which is input B. As you can see from our truth table, if you only enter the correct password but the fingerprint is wrong, this is a 1 and 0. The output remains 0 only if strictly denied. The system will output a true value of 1, unlocking the door only when both conditions are completely satisfied at the same time. On the flip side, page 11 shows a home security alarm which operates on an OR gate. Unlike the smart lock, a security alarm needs to protect your house from multiple angles. If a door sensor is triggered or a window sensor is broken, you want the alarm to go off immediately. Looking at the truth table, this one, if either sensor detect an instruction, meaning we get a 1 on an input, the OR gate instantly output a 1, triggering the alarm to protect the home. Finally, on page 12, we have automatic straight line using a NOT gate. We simply flip the input its exact opposite. During the daytime, the daylight sensor detect light, sending a true signal of a 1. The NOT gate inverts this to a 0, keeping the straight line off. When night falls and it becomes dark, the sensor drops to 0, and which the NOT gate flip into a 1, turning the straight line on automatically. Now to prove how this logic gate function in real-time engineering application, our group didn't just stop at paper theory. We designed an interactive logic explore program right inside MATLAB. Let me demonstrate our code. As you guys can see here, in the MATLAB command window, we build a guessing game utilizing this as a real-life scenario. If the user tests out question 1 for the smart door lock with a correct password but a wrong fingerprint, our logic code process it and precisely display correct fingerprint wrong, door stay closed. It dynamically evaluate the user understanding of the truth table we just went through.
So, before we wrap up, let's do a quick recap of all 6 logic gates that we covered today. First, the AND gate outputs 1 only when all inputs are 1. Like an ATM, you need both card and pin. Next, the OR gate outputs 1 when at least one input is 1. Like a smart light, it turns on if motion detected or switch is pressed. Then, the NOT gate, the simplest one. It just flips the value. 1 becomes 0 and 0 becomes 1, like automatic street lights. The XOR gate output 1 when exactly one input is 1. Both them output is 0. The NAND gate, opposite of AND, outputs 0 only when both inputs are 1. Everything else is 1. And finally, the NOR gate, opposite of OR, outputs 1 when all inputs are 0. 6 gates, each with their own unique behavior, but together they form the foundation of every digital device we use today. Thank you.